Well, greetings, Mr. Kolazar's class. We're going to start into section 5-2, and we're going to be looking at what's known as the parts of a wave, and then we're going to be looking at frequency, wavelength, and how they're related together as we're looking at calculations. And to begin with, we talked about the idea of the atom, nucleus, and then we've got electrons somewhere around this nucleus, and they continue to orbit around. And we're going to start to look at these electrons and where they actually are at and what we can decide to find out about them. Now, as we look into the electrons, our first idea is going to be electromagnetic radiation. Electromagnetic radiation is going to be abbreviated EMR. So electromagnetic radiation, form of energy that travels like a wave through space. Now, there are a lot of different varieties of electromagnetic radiation, including visible light, and we're going to point those out in just a minute. But one of the things that scientists do is the chemists might want to study the way matter interacts with light, and so what we can actually see. And now, light is just one of the electromagnetic radiations, but what we see is actually visible light, so it's a very small part of the spectrum. Now, what the spectrum is, the electromagnetic spectrum includes all forms of electromagnetic radiation of different wavelengths and frequencies. So a couple of things we could see down here. Visible light is just this little spot right here. So Roy G. Biv all fits into what we can actually see. Now, outside of what we can see, you might have heard of X-rays. X-rays, if you break a bone. Gamma rays you want to stay away from are much stronger in energy. And then over on the other side, microwaves used to cook our food, and radio waves. This is actually where television and cell phone waves are at, is in the radio waves category. So all of these different electromagnetic radiation waves are different forms of electromagnetic radiation. Now, when we look at a wave, there are a couple key parts we need to look at. The crest is going to be the top of a wave. So it's at the height of the wave is where our crest is. The trough is going to be the lowest part of the wave. And then our amplitude is going to be the height from the crest to the midpoint. So this will be the amplitude, or known as the height of the wave. And so that's just going to break us down crest, trough, and amplitude to make sure that you label and know those three parts of the wave. Now, as we look at the wave, there are a couple things to look at. First off, our wavelength. Wavelength is going to be represented by the Greek letter lambda. So now, when we think about wavelength, one thing we might do is if you just to look at wavelength, if you just put one wavelength, if you start to put a couple together, it kind of looks like an ocean wave coming in. So you might be able to remember wavelength with a letter lambda from the Greek alphabet. Now, it's going to be the distance between two equivalent points on a wave. So from one point to a second point, two equal points apart on a wave, or points, is how long one wavelength is. Common units, meters, centimeters, nanometers, are going to be commonly seen wavelength units. Frequency, then, is going to be the letter nu in Greek, which is presented with this little fancy V. It's got kind of a little tail up to the top of it there. And so that's going to be the letter nu in the Greek alphabet. And this is going to be frequency, how frequently, or the number of waves that pass a given point per second. So hertz is what we usually will measure in Hz, amount of waves per second is what it's known in. So in calculations, we'll express as waves per second, but usually waves is understood, so a lot of times it's just going to be known as per seconds. Now the two ways we can draw that is 1 over the number second, the unit second, or seconds to the 1 negative exponent. So it's said as per second. So when you say it, per second is what this one is. So example, 652 hertz would be the same as 652 per seconds, or 652 seconds to the negative 1. Both of those, or all three of these, are per second, is our second part, the frequency. Now when we look at a wave, if the wave, let's say from here is where we're going to start, in a second we'll just advance to see how many times we get to a second wavelength, or to a new wavelength. So as it moves, our second one, 2, and 3. So we'll start that just one more time. So 1 full wave, 2 full waves, 3 full waves. So we had 3 waves, or we call it 3 per second. Now the relationship between wavelength and frequency, if you look, we've got from one wave to the top of the next, one wave to the top of the next. This one is a much longer wavelength, much shorter wavelength. So what we're going to look into here is, as these two travel the same distance and time, that wavelength and frequency are going to be different between the two. So if we start to let them move, we've traveled a different amount. So this top one had a relationship of 3 waves to 2 waves in that time. So if we just were to check again, as they move across, the amount of waves that are completed are different. Now what we're going to look at is relationship between the two, wavelength to frequency. As one goes up, the other one must go down to keep us equal. We're going to call this an inverse relationship. So this is the important idea between wavelength and frequency, is that they are inverse of one another. Now, what do all forms of electromagnetic radiation have in common? They all travel as a wave. They all travel the same speed. And they don't need particles to travel through. So they don't need a medium to travel through. An example is sound needs air or a solid or a liquid to travel through. Light does not. So light does not need a medium. Sound would need a medium to travel through. Now, a relationship between these. We have this equation to write in at the bottom of the page. Our equation to write in has 3 parts. C is going to be known as the speed of light. From there, lambda multiplied by nu always equals C. So our equation, you'll need to write these variables down, and our equation is there. Now, C, the speed of light, is a constant. So it's a constant 3.0 times 10 to the 8th meters per second, which is really fast. And it's always going that same speed in a vacuum. Now, if we were to look at that, that's about 671 million miles per hour is the speed of light, or 3.0 times 10 to the 8th, about 4 times around the world in 1 second. Now, to use that equation, what we're going to look at is the idea of, if one of those variables changes, how does the other variable change? So we will always be given either frequency or wavelength and have to solve for the other one. We know the speed of light. So in our first question, it says radio waves are used to transmit information on various channels. Calculate the wavelength of a radio wave that has a frequency of 5.4 times 10 to the 10th hertz. Now, what we're going to look into is our first step, since we're solving for wavelength. Wavelength is going to be equal to the speed of light divided by the frequency. So all we've done is move our equation over to what we want to solve for. We know speed of light, 3.0 times 10 to the 8th meters per second. And we know our frequency, 5.40 times 10 to the 10th hertz. Now remember, we said that hertz could be written as per seconds or seconds to the -1. Reason we show that is that our units can cancel our units. Now when we type that in, as we're looking, remembering back 3.0, and then we're going to use that exponent EE key, times 10 to the is what that stands for, eighth, divided by, and our second one we had was 5.40 times 10 to the 10th, exponent EE 10. And we get about 0.00555 repeating. So our answer, oh, we want one more zero in there, 555 repeating, and our units left over are meters. Since we're calculating in a wavelength, meters is what we'd want to see there. And our last problem, microwaves. Used to heat water which cooks food in a microwave. Calculate the frequency of a microwave that has a wavelength of 3.0 times 10 to the negative 2. So what we're going to look at this time is our equation C is equal to lambda times nu. This time we're looking to solve for frequency. So C over lambda is what we're going to use as our equation. We know C is the speed of light. 3.00 times 10 to the 8th meters per second. We know the wavelength, 3.00 times 10 to the negative 2 meters. And so when we look to solve this time, we're going to end up meters canceling meters. So just leaving us with a per second unit. 3.0 times 10 to the 8th divided by 3.0 times 10 to the second. Make sure your calculator is coming up with this answer. You should get about 1 times 10 to the 10th. Now our units for this could be per second, would be acceptable, or we could use 1.0 times 10 to the 10th seconds to the minus 1, or you could even use the unit hertz in the end. Now when we compare these two relationships between frequency and wavelength, as we look at those two problems, the idea is that remember that they are inverse. Ooh. So if we were to look at those numbers, the wavelength in the first one, so if we look at that first one, wavelength in 9 was a little bit larger and our frequency was a little bit smaller. In that second problem, our wavelength is a little bit smaller and our frequency was a little bit larger. Now in the end, the speed was still the same. So we had the same speed, just different wavelength and frequencies. So if we went back to that diagram to begin with, relationship between wavelength and frequency, even though the waves are traveling different wavelengths and different frequencies, they're traveling the same speed when arrive at the same point at the same time. That'll finish up our waves.